theorem and its applications. The important application of Gauss theorem is we get the equation for electric field at any point by numerous charges which are continuously distributed. These charges are distributed in three different fashions. One is linear charge distribution, surface charge distribution, and volume charge distribution. In the last class, we got the equation for linear charge distribution. Today, let us see what is the equation we get for surface charge distribution. The surface charge distribution. Here we have three shapes, that is two shapes of surface charge. That is a planar shape, the planar shape which may be of any shape. Planar means circular, rectangular or any other shape, but with planar shape. And other is spherical shape. This is planar shape. This is spherical shape, a sphere like, just like a ball like. The charges are on the surface of the sphere. The charges are on the surface of the plane. The plane here taken circular plane. So this is a surface charge. Let us see what is the equation for the electric field by a point by this distribution, this type of distribution. This is a planar distribution and spherical distribution. So let us see what is the equation for this. Look at this equation. I have taken circular shape, the plane containing a circular shape. All this surface is saturated by the charges, plus Q charges. If the surface, plane surface is a continuous charge distribution, what would be the direction of the electric field? First, we have to find out what would be the direction of the electric field. By this surface there is charge. The electric field is always perpendicular to the plane. That is a plane. Surface plane is there. So it is the surface, a thin plane on which charges are distributed. Perpendicular means this is a perpendicular direction and away from the surface. It is a direction away from the surface. Here the surface, the perpendicular direction is, you have both sides are possible. This is one side and also back side like this. Away from the surface. That is the direction like this. These lines are perpendicular to the plane and away from the surface. Perpendicular. So this is the only possible direction of electric field. But electric field is not in this direction or any other direction. Electric field is always perpendicular. Electric field direction is perpendicular to the plane on which charges are distributed. This is the direction of the electric field. So there is an important point we need to know. And let us go for derivation. This plane here kept and the point is here where we need to find out the electric field at this point by these surface charges. What is the idea using the Gauss theorem? You have to think about what would be the possible geometry of Gaussian surface. The possible geometry of Gaussian surface, that is enclosed surface, which encloses these charged surfaces, the charged surface, and also the point on the Gaussian surface. This Gaussian surface should have that point. The point should be on the Gaussian surface. Like that, when you imagine, that is, just think about it. What would be the possible geometry we can able to draw about this, so that the charges are completely enclosed in it, and also point is on the Gaussian surface like this. That is the possible geometry we can have. What is geometry? A cylindrical shape, the cylinder enclosing this plane, circular plane, and these ends are open, should be closed by what? That is two planes, that is just like the circular plane like this. These ends are closed by circular planes like this. And this plane and this plane and this plane, look at that, have the same shape and size, no difference. And this shape is cylindrical shape enclosing. So with this, what is that? This diagram or surface is called as Gaussian surface. This circular surface and this surface, that is the cylindrical surface, that is all over, no, cylindrical surface, and this is circular surface, this is circular surface closing. This is the Gaussian surface. So this Gaussian surface is enclosing all these charges, and the point is on the Gaussian surface, that is surface of this circular plane. So with this diagram, let us see that the surface is not, there is no symmetry. There are three different surfaces. That is one surface, another surface, and one more surface like this. These surfaces are circular plane, that is circular planar. This surface is cylindrical. Three different surfaces. So let us call this as, that is 3, that is surface 1, surface 2, surface 3. Three different shapes of surfaces. And after just with electric, that is area, that is electric field vector direction, we need to understand the area vector direction. Whenever you draw any surface, the Gaussian surface, so what would be the possible direction of the, that is field direction inside this, and what would be the area vector of each surface? So this area vector of this surface is this. This is normal to this plane. As you know, area vector is always perpendicular to the plane. So this is the area vector. This is the area vector. And what is the area vector of the cylindrical shape? At every point, so right, draw perpendicular to this. This is the direction of the area vector of the cylinder outside. Any point on the cylindrical surface. Area vector direction on the cylindrical surface. So with this idea, let us go for what is that derivation or equation that we get from the application of Gauss theorem. That is the Gauss surface. Apply the Gauss theorem. What is Gauss theorem? That is the integration of, that is differential form d eta. That is for a differential. First always commence with a differential equation. This represents what is Gaussian surface or circular is closed surface integration. So this entire, that is the flux, that is fluxed by the entire surface is there are three different surfaces. It is sum of the fluxes of all the three surfaces. Flux by this, and flux by this cylindrical surface. Therefore, we have three different equations. This is the equation for a flux on the surface, to the surface, is it right? So this is the equation for this surface, this is the equation for this surface, this is the equation for this surface. It is integral of the field vector, that is field electric field, and it is a area vector in differential form, because I have taken differential form only for the area vector, not for this electric field. Area vector on cos theta. What is theta? Theta is the angle between this vector and this vector here. So now with this equation, that is flux, that is entire flux of the entire Gaussian surface is equal to sum of the fluxes of this surface, and cylindrical surface. Next, go for simplification of this equation. First, think about what is the theta for this. Look at this. This surface and this surface. That is the direction of electric field. That is the direction of the area vector. Both are same. So these vectors are coincided. Theta equals 0. Similarly, this vector is coincided. Theta equals 0. But this vector, look here. This vector and this vector, field vector and area vector, are perpendicular to each other. That is 90 degree. Theta equals 90 degree. Then this cos theta equals 0. This cos 0 is equal to 1. Reduced to 1. So cos theta is 1. Cos theta is 1. And after integration of this, d becomes s. ds2 becomes s2. Integration of this, d becomes eta, like this. Integral equation. 0. So with this equation, let us know what is S1. It is the total surface area of this plane. What is S2? Total surface area of this plane, enclosing this. But look at this. This one and this one. These have same shape and size, no difference. Therefore, they have same surface area. And this plane have same shape and size. Therefore, surface area of this remain same. This is surface charge I have taken, on which charges are distributed. So S1 equals S2 equals S. S is the surface area I have taken as S. Then simplify. That is eta is the total flux by the Gaussian surface. It is the one from Gauss theorem, Q by epsilon naught. That eta is equal to Q by epsilon. What is Q? Total charge that is distributed on the surface. Q is the total charge distributed on this surface divided by epsilon naught. So that reduced to S1, 2 ES. ES plus ES, 2 ES. What is S? S is this is both surface areas. All are same. And we know that what is that? That is a charge distributed on the surface. So let us write one more equation. As you know, it is the charge density for this surface charge. Recall the previous equation. Charge density is equal to Q divided by surface area. What is Q? The amount of charge distributed on the surface. What is S? The surface area of this I have taken here. Surface area is S. So write Q in terms of these two. Surface density, that is surface density into surface area. Substitute this into this equation. Q is equal to, that is sigma S. And simplify, solve for E. That is SS cancel, because surface of this is same as surface of this. E is equal to sigma by 2 epsilon naught. So this gives the magnitude of electric field. What is E is equal to? Magnitude of electric field at this point by this surface charge magnitude. It depends on, the magnitude depends on only surface density of the charge. But this electric field is not depending on the distance of the point from the surface, whether it is here or away or any. It is independent of the distance from the surface. Therefore, it is depending on only the surface density of the charge. Higher the density, higher the potential at the point. It is the magnitude of the electric field. So what is the next equation? Since this electric field is a vector, so vector form of electric field is this, magnitude into unit vector. This unit vector represents the direction of electric field. So direction of electric field is this. This is the direction of the electric field, same as area vector. So it is scalar form, vector form. That is magnitude and vector. So this is easier to get what is that equation for electric field using Gauss theorem. Only thing you have to think about what would be the possible geometrical shape for the set I have chosen. This is a surface charge, this is a point. This is a geometry, that is a possible geometry of that Gaussian surface. That is about the planar surface. If you have taken a rectangular surface, suppose rectangular plane, you have to take what is that? A rectangular shape of this, like this, just similar to the cylinder. And rectangular shape of this, what is that? Plane closing this. That also be the same mathematics. Here there is no field direction remains same. So when you take that shape, then you get the same equation like this. Whether the shape is a circular or what is a rectangular shape or square shape or some other shape, but should be plane. Except what is that? A planar surface. That is the one. Next is, let us get the equation for spherical shape. That is a spherical shape. That is a sphere, a spherical or ball like. The charges are distributed on the surface. Let us go for the equation for what is that electric potential at a point by this set of charges. So there are two possibilities. A point we can place here. This point is placed outside the spherical, what is that? Surface. Outside the surface charge, that is point is outside the surface. And one more diagram is there, the same diagram. That is a spherical surface, charges are distributed, but the point I have taken inside the sphere. Difference here, the point is taken outside the sphere, only difference. What is electric field? If the point is outside the spherical charge. What is the electric field? If the point is inside, anywhere inside the electric, that is inside the spherical charge. So let us go for E, derivation for E. If you have taken the point here outside the spherical shape, then again you have to think about what is the possible geometrical shape of the Gaussian surface we can draw about this set, that is so that the Gaussian surface encloses completely these charges, and also the Gaussian surface should contain this point. That way is the diagram we need to draw. Look at that, it is drawn. So this is a possible diagram we can have with this set. What is the diagram? There is one more spherical shape, that is area, one more sphere of area, one more area of sphere like this. No charges here, here charges here, spherical shape. So here point is on the surface. So now we can see that is the R is the radius of this sphere. This is a Gaussian surface. This is Gaussian surface. This is spherical surface where charges are distributed. Radius of the Gaussian surface is R, and radius of this also sphere, no, radius of the spherical surface is R, capital R, for the difference. And one more point, then after this drawing Gaussian surface, we have to think about what is the direction of the electric field and the area vector. Direction of the field and area vector. So at every point here, the electric field is not in this direction. Electric field is away from the surface where the charge is distributed and perpendicular to the surface like this. Every point, no, there is a perpendicular direction at every point. But this direction is not towards the inside. It is away from the surface like this. So every point it is, electric field is direction like this, distributed in all direction possible. So if we this point there is electric field in this direction. At this point, what is the area vector? This area vector, these two vectors are in the same direction, theta equals 0, but showing this for derivation purpose like this. So at every point on this sphere, at every point in the brain, the area vector, electric vector are always getting coincided. For infinitesimal area you have taken, you get infinitesimal flux you get, of course. That is the equation you take. So at this point, what is the flux? That is that is electric field is this, and the area vector is this. So let us calculate what is the total flux by this Gaussian surface. That is total flux. That is in the differential form. This is the one equation here. And here surface is not two or more. It is only one type of surface, spherical surface. Only one surface all over. One type of surface, spherical shape. So this surface, so that is flux, that is total flux by the Gaussian surface is equal to flux by, what is that? Surface is only one. Yes, ds stands for, that is S stands for surface area of the sphere, this sphere. Cos theta, theta is the angle between this vector and this vector. I told you at this point, this vector and this vector coincided. Theta is equal to 0, cos 0 is equal to 1. And integration, but is for a finite, but is for a total flux. Every point you have this flux. For a total flux by the Gaussian surface is integration. Integration of this, integration of this. This becomes eta, this becomes ES, total surface area of the sphere. The total surface area of the sphere is equal to 4 pi r square, where r is the radius of the sphere. 4 pi r square, total surface area of the Gaussian surface, not the spherical surface. Substitute for this and apply the Gauss theorem. That is, for a closed surface, this flux is equal to Q divided by epsilon r. What is Q? Q is a total amount of charge that is distributed on this entire spherical area. Q divided by epsilon r. Then solve for E with this. E is equal to, we get this. Taking this on the left hand side, you get this. And in this now 1 over 4 pi epsilon naught, we can write it in the form of what is that? Coulomb's constant. That is known. So E is equal to KQ divided by R square. So look at this final equation. Electric field at this point. What is the electric field at this point by the entire set of charge that is in a spherical shape is equal to Q into K into Q divided by R square. Coulomb's constant into amount of charge it is present over there divided by R, distance between the, that is the sphere of charge and the point. It is from the center of the sphere and this point R square. That is the magnitude of the electric field. But in the vector form, it is the one, it's the same magnitude into unit vector. What is unit vector? Vector direction is this. So unit vector represents the direction of the electric field. So this is how we can arrive at the equation like this at the easiest way. If you go for what is that? Using application of Gauss theorem. So these equations you have got also by other alternative method, but it is very tedious. The steps are becomes and the problem not tedious but is laborious. More number of steps and includes what is that mathematics, that is a lengthy mathematics is involved. So this equation already we have, just recall that equation. This equation is similar to the point charge. This electric field by a point charge. The same equation, just recall that somewhere in the previous class I have given this equation where Q stands for electric charge. What is that? Electric charge by a point, what is only one unit charge. only one positive charge per unit charge. But here charged by all the positive charges. Entire. So amount of Q, it is a charge by all the positive charges. For a point charge, it is only charged by one positive charge. That is the only difference. Same type of equation you get for what is electric field by point charge as well as electric field by what is that? Spherical distribution. So that is what easier to get the equation using Gauss theorem. So next is the last one. The same what is that I written in bigger size, there is only difference. It is spherical distribution of charges. The point is taken inside. So it is a charge and the point. What would be the possible diagram? Again you think about what is a possible diagram which can have, that is that the Gaussian surface can have this point like this. So this is the only possible diagram is possible. That is again what is that? Spherical shape. Spherical shape having a point on the surface. Anywhere on the point you can take this point. But this spherical surface will come inside this sphere. That is the only difference. But you can have, it is not possible to have, but here it is no geometry. It is not possible to have this point on the surface and including all the charges. It is not possible. Only this is the possible diagram. There is a Gaussian surface. That is a surface charge, spherical surface charge. That is the only difference. As you know, this is R is a radius of the spherical charge. This small r is the radius of the Gaussian surface. That is the imaginary surface. Point is here. So let us calculate what is that. What is the potential? What is the electric field at this point? Electric field at the point is just recall that same mathematics. So electric field by at the point is this differential equation, and electric field by the entire surface is different integral equation. So Q the eta is equal to E into S, electric field into surface area, Gaussian surface area, not the surface area, Gaussian surface area. And here flux is, just imagine what is the flux with this Gaussian surface. The flux is equal to, what is that? 0, because the charges are not inside, the charges are outside. So the charges, Gauss says that only the charges when enclosed flux to the surface, that is the one. But the charge inside the Gaussian surface is 0. But all charges are outside. That is why Q is equal to 0. So this is what is that? Q is equal to left hand side is 0. That is 0 is equal to S. Finally what is E? Equals 0. Look at that. If you have a spherical charge, if you take any point inside, no electric field. But if you take any point outside, electric field is applicable. But electric field at the point, look at that. Electric field at the point with this shape, it depends on what is that amount of charge, what is distributed, and also distance of separation. So as the distance increases, the electric field decreases. As the amount of charge increases, electric field increases at the point. So look at the difference here. In this case, electric field is not depending on the distance between the point and the surface charge. Here, electric field is depending on, what is that? Distance between the point and the surface charge in this spherical shape. Look at that. These are the equations you get. So these are the applications of Gauss theorem.